Good evening, everybody. Let us start with the class. Good evening, everybody. Am I audible to all? Good evening, everybody. Good evening. Good evening. So let's start with the class. So today I would be discussing about Atterberg limits. Very interesting topic. So this we will cover in two parts. Today I will cover the part 1, and in the next class I would be covering the part 2. Okay. So let's see Atterberg limits part 1. Let's talk about Atterberg limits. These are also known as consistency limits. These Atterberg limits are also known as consistency limits. So, how would you define consistency of a soil? So, consistency is nothing but the measure of firmness of the soil. It measures the ease with which we can deform the soil. If the soil is soft, its consistency is soft, then you can deform it easily. If the consistency is stiff, you will have to apply more energy to deform it. So, consistency just describes the firmness of the soil in terms of description such as the soil is soft, firm, stiff, hard or very stiff, etc. Okay. So, it indicates the relative ease with which you can deform the soil. Now, this consistency is defined for clay soils obviously, because the engineering behavior of clays depends upon water content. Now, to define these consistency limits, we define 4 states of clay. What are those 4 states? The 4 states are known as what? Solid state, semi-solid state, plastic state and liquid state. As the water content increases, the soil moves from solid to semi-solid, then to plastic, and if you add excess amount of water in soil, it will behave like a slurry, that is, it will be in the liquid state. So, now water content, the boundary moisture content between any of these state is actually known as the Atterberg limit or the consistency limit. For example, Atterberg have given us a chart like this. See, Atterberg have given us a chart like this. Please see this chart. So, Atterberg have given us a chart like this. This is the graph given by Atterberg. Okay. Here I would be plotting volumes and here I would be plotting water content. So, when the soil is completely dry, it will have some volume. In its words, there will be only the what? There will be only the air would be there, but it will have some volume, that is the dry volume of the soil. As you increase the water content, what will happen? The soil will become partially saturated, and there will be a water content at which my soil is just saturated, means all the voids will be occupied by water only. Beyond that, if you increase the water content, what will happen? The change in volume will be proportional to the change in moisture content. Got my point? So, this is our Atterberg chart. Now, on this Atterberg chart, the boundary moisture contents are defined like I am showing here. These are the boundary moisture content. Okay. So, here this is VD, that is the dry volume of the soil. As you increase the water content of the soil becomes partially saturated, and then by reaching here it will be just saturated. After this, if you increase the water content, there will be proportional increase in volume. So, this is my plastic limit, this is my liquid limit. So, here I have the solid state, here I have the solid state, then I have the plastic state, then I have the solid state, then semi-solid state, then we have the semi-solid, and then we have the plastic state, and finally I have the liquid state. And these moisture content at the boundary of any two states are known as the consistency limits. WS is the shrinkage limit, WP is the plastic limit, and WL is the liquid limit. These are known as the Atterberg limits of the soil, and these are determined using what? Using the some experiments, and those experiments are done on soil sample finer than 425 microns. Means first you will take the 425 micron sieve. On that soil you will conduct the test and you will find out these water contents. Okay, we will see one by one all the experiments also in detail. Let's read what is given in the PPT. So, consistency is used to describe the firmness of soil in terms of description such as soft, firm, stiff or hard. It indicates the relative ease. It indicates what? It indicates the relative ease with which a soil can be deformed. Consistency limits are used for classification of fine grained soil, especially clays. So, these will be used for classification of clays, for defining the index properties of clays. Since water content influences the consistency of clays, like I said, the consistency of clays depends upon the water content of soil. So, the following states are used to describe the consistency of clay soil. What are those four states? Solid, semi-solid, plastic, liquid. As water content increases, soil move from solid to semi-solid state, then to plastic state and finally to liquid state. The boundary water content at which the soil changes its state are called consistency limits. So, the boundary water content between any two states are known as the consistency limits, and there can be only three consistency limits. These are also known as Atterberg limits, that is shrinkage limit, plastic limit and liquid limit. Okay. So, the boundary water content at which soil changes its state are called consistency limit or Atterberg limits, and it is determined for soil samples finer than 425 microns. So, Atterberg says that it will be conducted, the experiments that we are seeing will be conducted on soil samples finer than 425 microns. Okay. So, this is our consistency limits. Now, one by one I will show you all the consistency limits. First, please take down till here. Please see till here. If you have any doubts, please ask me. See this graph, then I will talk on this graph only once again. So, please see this graph once, then I will proceed further. Okay. Please see this graph, my dear friend, then I will proceed further. Okay. Please see to it. Let us see. Now, one thing you should understand, that at all these consistency limits, the soil is saturated. At shrinkage limit, the soil is just saturated, whereas at plastic limit and liquid limit, the soil is oversaturated. So, here the soil is oversaturated. Okay. So, here the soil is oversaturated. This is Vp and this is Vl. So, Vp is the volume at plastic limit, Vl is the volume at liquid limit. Since this is a straight line, so from the slope of the straight line, I can write a formula. What? Y2 minus Y1, that is from the slope I am writing this formula, Y2 minus Y1 upon WL minus WP, right? X2 minus X1 is equal to VL minus VD upon WL minus WS, or I can rearrange it as well, that is VL minus VP upon VL minus VD. If any unknown is there, we can just find the unknown as well using this formula, and you do not have to remember this formula comes from the slope of the straight line, right? This formula just comes from the slope of the straight line, right? Got it? So, we can go for it, right? Very good. Let us proceed. Any problem till here? No problem. Very good. Now, first I will talk about the liquid limit. Today we will talk about liquid limit in detail. So, what is liquid limit? Represented by a symbol WL. So, liquid limit is the boundary moisture content between the liquid state and the plastic state. Beyond liquid limit, the soil will be in its liquid state, means it will lose all its shear strength. It will behave like a slurry in the liquid state. So, at this water content, shear strength of soil is very negligible, around 2.7 kPa. So, means all the soils have the same shear strength at liquid limit. Please remember this, because this will be the basis of our experiment. All the soils have same shear strength at liquid limit, and that shear strength is very negligible at around 2.7 kPa. And the soil offers practically no resistance to flow, means it can easily flow. Shear strength is negligible. Liquid limit of the soil is determined using two experiments. Today I will be seeing only one, that is the important one. One is the Casagrande's tool and second one is the cone penetrometer method. Any of the method you can use to determine the liquid limit of the soil. So, let us talk about the Casagrande's tool in detail today. Okay. So, it is the boundary water content between liquid and plastic state. At this water content WL, shear strength of soil is negligible, 2.7 kPa, and it practically offers no resistance to flow. WL is calculated using the Casagrande's tool and the cone penetrometer method. Today I would be discussing the Casagrande's apparatus or the Casagrande's experiment in detail. Okay till here, no problem. Now let us talk about the Casagrande's experiment in detail. So this Casagrande's experiment you have done in lab as well, I guess. So this Casagrande's experiment you might have done in the lab as well. So this is the Casagrande's tool. We have a Casagrande's bowl here. So what we do here? Let us see what is the experiment that we will do here. Very simple experiment. So you will take the Casagrande's bowl. First you will make the soil paste. You will add soil, you will add water and make a soil paste. Mix soil and water and make a soil paste. And make the soil paste. Now fill the soil paste in the Casagrande's bowl. Fill the soil paste in what? Fill the soil paste in the Casagrande's bowl. In the Casagrande's bowl, you will see a marking. Till that marking, fill the paste. See, in the Casagrande bowl, you will see a marking. Till that marking, you should fill the paste. Okay, like this. Now attach this Casagrande bowl on this apparatus. Casagrande's apparatus. There is a handle here. and here you have a rubber pad as well. Here you have a rubber pad as well. Okay, we will have a rubber pad here. This is the rubber pad. Before attaching this 𝐂𝐸𝐵 ball with soil on this rubber pad, make a 2 mm groove here. See, with the help of this 𝐂𝐸𝐵's groove cutter, you will make a groove. See, this is a groove cutter. You don't have to remember all the dimension, but the groove that it will cut will be having a dimension of 2 mm. So, like this, you will cut a groove in the soil. Okay, this will be the groove that you will cut in the soil. Got my point? And you will start giving blows. You will start giving blows just by rotating. Once this handle, what will happen due to the cam assembly? This ball will rise and will have a free fall on this rubber pad. And when this ball collides on the rubber pad, what will happen? The soil will get disturbed. It will start flowing. Now, if you have rotated once, number of blows is 1. 2, second time rotation, 2 blows, 3 blows, 4 blows. Like this, you will keep on giving the blows until this cavity, the 2 mm groove that you have made, fills. It should fill, means the soil will flow and will join here. So, if the soil joins or if the groove closes up to a distance of 12.7 mm, we will close the experiment and we will record the number of blows. Okay, and this you don't have to measure from any scale or something, just by observation you can see whether the groove is getting closed up to a distance of 12.7 mm or not. So, once the groove gets closed up to a distance of 12.7 mm, we will close the experiment, we will record the number of blows, and we will take a small quantity of soil from here, place it in the oven and find out the water content. So, you recorded the water content as well as the number of blows. So, water content as well as the number of blows we have recorded here. So, we have recorded the water content as well as the number of blows. Okay. So, this is the experiment. Now what you will do here? Now, we have not found out the liquid limit till now. 𝐂𝐸𝐵 says that liquid limit is the moisture content at which 25 number of blows closes the groove of 2 mm. So, now to find out the liquid limit, we will have to do this experiment once again with different water content, and we will find out the number of blows again, and this whole data will then be plotted on a semi-log paper. We will conduct this experiment twice. You will record 2 water contents, W1 and W2. As you increase the water content, what will happen? More is the water content, lesser will be the number of blows required to close the groove. If W1 is greater than W2, then N is the number of blows, N1 will be less than N2. Take this 2 data on a semi-log paper, because on the semi-log paper only you will get a straight line, and this is experimental. Therefore, I am using the semi-log paper, and on the straight line only the interpolation can be done. Okay. So, we have experimentally it has been seen that the data comes out to be a straight line if it is plotted on a semi-log paper. So, therefore, we are using semi-log paper here. So, 2 data I will use corresponding to W1 N1 and W2 N2, and you will make a straight line. And then you will find out the water content corresponding to 25 number of blows, and that water content is actually known as the liquid limit. So, this is how you will find out the liquid limit using the 𝐂𝐸𝐵 tool. Very simple experiment. So, this is all written also. So, in this case we use a soil sample and add sufficient moisture to it. The sample is then put in 𝐂𝐸𝐵 bowl and a groove of 2 mm is cut. The bowl is given blows on a rubber pad, and number of blows N required to close a groove of 2 mm for a distance of 12.7 mm is noted. So, groove dimension you should remember, that is, it is 2 mm groove. The graph is plotted between water content and number of blows on a semi-log paper like shown. From the graph, moisture content at which 25 number of blows closes the groove is noted, and this moisture content is actually called liquid limit moisture content, that is WL. Now, the straight line that we have obtained here is known as the flow curve, and negative of this slope is known as flow index. So, magnitude of slope of the flow curve is actually known as flow index. That is, IF will come out to be how much? That is, IF will be equal to IF is always positive, but the slope of this straight line will be negative. So, negative of the slope will be log n2. So, negative sign I am already adjusting it. Log A minus log B is log A by B. So, this I can write like this also, W1 minus W2 is equal to log of N2 by N1. So, this is the flow index IF will be defined like this, very simple. And this IF is inversely proportional to the shear strength of the soil. For a given soil, IF is constant, but if you change the soil, IF will change. Please take down till here, then I will show you the significance of IF. Please see till here, and any doubts, then let me know. Then I will show you the significance of IF as well, okay. Please note it down till here, then I will proceed further again. Please see till here, any doubts you can ask me, then I will proceed further again. Done till here? No doubts. Very good. Now let us take two soils. Both the soils will have different IF value. Soil 2 have more IF, soil 1 have lesser IF. So at same moisture content, if you will see, soil 1 takes large number of blows and soil 2 takes lesser number of blows, and number of blows is directly proportional to shear strength. So soil 1 will have more shear strength as compared to soil 2. So IF2 is greater than IF1, but N2 is less than N1. Means shear strength of soil 1 is more than shear strength of 2. So I can say that IF is inversely proportional to shear strength of soil. And the above approach of determining WL is known as the 2-point method, because at least we require 2 points to find out the straight line, and from interpolation we will find out the liquid limit of the soil. Let's do some numerical on this concept, then I will proceed further. Okay, let's do a numerical on this concept. See, please solve this numerical one. Please solve this numerical, then I will proceed further. Okay, please solve this numerical, my dear friend. Please solve this. Okay, let's see. Please solve this numerical, please. Make it fast. Take your time, do it fast. Let's begin. Let's see the solution of this question. Very interesting question. Let us see this question once again. Let us begin. Let's see the solution. Okay, my dear friend, let us see the solution. So, saturated clay sample has a volume of 20 centimeter cube, that is 20 cc. So, we have the volume of saturated soil sample at its liquid limit. So, VL is given to me. Let us see the solution of this question. Very interesting question. So, volume of the soil at liquid limit is given to me, that is 20 cc. The water content corresponding to the liquid limit is 40%. So, WL is given to me, that is 40%. During drying, the sample reaches its shrinkage limit, its dry volume VD becomes 40 cc. VD is 14 cc and shrinkage limit I need to find out, I guess. Okay. If the total dry mass of the soil sample, weight of soil solids is VD is given to me and weight of soil solids is how much? 25 grams. Gamma W I will take as 1 gram per cc only. Okay. Everything is in gram cc. The shrinkage limit of the soil is, we have to find out the shrinkage limit of the soil. Let's try to find this out. Okay, very simple question. Let us try to find this out. So, we have to find out the shrinkage limit of the soil. Let's try at shrinkage limit. This is weight of solids, WS, capital WS. This is weight of solids. So, weight of solids is given to me and liquid limit is given to me, shrinkage limit we have to find out. So, let's try to do this question. Very interesting question, but very simple. If you want to try, still if you want to try, you can try it out. Rest I will do it for you. Okay. See now, we don't know the GS of the soil. Here I don't know the specific gravity of soil solids. So, by any means, if I can find out the volume of the soil solids, it will be done. Let's see how we will find out the volume of the soil solids. At liquid limit, my soil is saturated. This is at WL, at liquid limit. Okay. This is my liquid limit, solid, water. We know the weight of the solids, that is WS. Weight of water will be how much? WL into WS. Volume of solids I don't know, we have to find out this volume of solids. Volume of water I can find out, that is WL WS upon gamma W, and this is nothing but my VL, that is volume at liquid limit. From here, first find out the volume of solids, then using this volume of solids for VD I can find out the shrinkage limit also. Very simple. See now, VL, that is VL will be equal to what? That is VS plus WL into WS upon gamma W. So, VL is how much? 20. VS. WL is how much? That is 40%, 0.4. Weight of solid is 25 gram per cc upon gamma w. So this implies my Vs will come out to be how much? Please solve this, find out the value of Vs. What is the value of Vs you are getting? Tell me fast, my dear friend. 20 minus. Very beautiful question. Very interesting question. So Vs is coming out to be 10 cc. Now add shrinkage limit again. Use the same diagram. At shrinkage limit also my soil is saturated, it is just saturated with volume is equal to Vd, solid water. Weight of solids will be the same. Weight of water will be shrinkage limit into weight of solids. Volume of solids I already know. Volume of water will be how much? Ws into capital S upon gamma W, and this total is Vd. This is what? This is Vdn. Use this. So Vd will be equal to how much? Now Vd will be equal to Vs plus Ws into weight of solids upon gamma W. Vd is how much? Vd is 14 cc. 14 is equal to 10 plus shrinkage limit I have to calculate into 25 upon 1. So this implies shrinkage limit is how much? 4 divided by 25. 0.16. That is equal to 16% is the correct answer. So 16% means how much? That is B is my correct answer. Very good. Sakshi ji have given me the answer. Very good. Interesting question, right? So like this, using the phase diagram approach, you can solve this numerical. But for solving the numerical, you should understand that at shrinkage limit, the soil is saturated, as well as at liquid limit, the soil is saturated. So using this phase diagram, you can easily find out the shrinkage limit of the soil. Not a problem. Let's do one more numerical. One more numerical. Please solve this as well. Solve this as well, please. Make it fast. Do it fast, please. Do it fast. I am waiting, giving you 2 minutes time. You have to find out the liquid limit of the soil. Flow index is given to me, I guess. No, flow index is not given to me. Just interpolate and find out the liquid limit of the soil. Do it fast. Please solve this. So let's solve this question. Let us solve this question. So during a Casagrande's limit test, a clay soil sample, the following observation were recorded. So at a moisture content of W1, W1 equal to 50%. N1 was how much? 16 blows. And at moisture content of 38%, N2 is how much? Obviously, N2 will increase, water content have decreased, N2 is 40%. Sorry, N2 is 40, number of blows is 40. So, corresponding to 25 number of blows, we have to find out the liquid limit. So, for liquid limit, we have to find out corresponding to NL of 20, just interpolation. Now, IF is equal to what? W1 minus W2 log of N2 by N1 is equal to WL minus W2 log of N2 by NL. Substitute everything, you will get the answer, that is W1 is 50% minus 38% log of 40 by 16 is equal to WL minus 38% log of 25 by 16, correct. Find out liquid limit in percentage from here. You can easily find out just by interpolation. Liquid limit is coming out to be how much? Tell my dear friends, please tell me. Tell me please. We will solve it, answer will come out to be 44.2%. Just interpolation, nothing else. IF will be equal by in all the data. So B is the correct answer. Very simple question, 2-point method. just we have interpolated here, है ना? Using this graph only. First I have taken these two readings, then these two readings. Slope will be same. That's it, and you can find out the value of WL. This is my Telegram channel. You can always join in here to clear any queries that you have. Yes, tomorrow I will cover at a work part 2, where we will be covering the plastic limit as well as the shrinkage limit. Okay. Bye bye everybody. Take care.